A very good morning. Today we'll be discussing about the remote sensing applications in civil engineering. The unit 1, which is the introduction to remote sensing, and the course contents are basics of remote sensing systems, the EMR interaction and its characteristics with the atmosphere and the Earth surface feature, the platforms and sensors which are available in the remote sensing system, the sensor characteristics and the scanning. So what is remote sensing? So it is the acquisition of information about the object or a phenomenon without having a physical contact with the object. So in contrast to in situ or on-site observation. So this term is especially used to acquire information about the Earth and also the other planets. So basically remote sensing is used in numerous fields including geography, surveying, earth sciences like geophysical exploration, hydrology, meteorology, oceanography, etc. So basically, the process of remote sensing starts with the energy source or illumination. So either the sun will be the source of energy or a illuminating source will be acting as the energy source. So this source will have radiation in the atmosphere and it will be interacting with the target, and then the energy will be recorded by a sensor which is placed in the platform. And then the transmission, reception, and processing will be happening in the remote sensor. And this data will be used for interpretation and analysis. And after analysis, the data will be used for different applications. So what is energy source? The primary source of energy that illuminates different features on the Earth's surface is the sun. So this sun's energy source will be used as the source to capture the information from different targets. Although the sun produces electromagnetic radiation in a wide range of wavelengths, the amount of energy it produces is not uniform across all the wavelengths. So other than the solar radiation, Earth and the terrestrial objects are also the sources of electromagnetic radiation. So once when the radiation and the atmosphere are in contact, so it emits different sources of energy which will be hitting the target in the earth as well as in the atmosphere. So once the target is hit by the energy source, for example, buildings, roads, grass, forest, etc. So the energy will be transmitted back, that is reflected back as a solar radiation to the satellite, and then the satellite will be transmitting this information to the reception and processing in the ground station. So this ground station will be processing all the data which are transmitted from the satellite, and this will be used for interpretation and analysis, and final output will be the applications in the various fields. So what will happen when there is an interaction with the target? So the electromagnetic source will be sending signals, that is energy source will be sending signals to the target, and once it is reaching the target, it will be reflecting back. So what is happening before it is reaching the target? So the first source of interaction of the EMR source will be the atmosphere. So in the atmosphere, it will be interacting with some particles like dust particles, clouds, etc. And then there some absorption and scattering will take place. And then after it is passing through the atmospheric particles, it reaches the ground. And once when the target in the ground is hit by the energy source, the scattering, emission, absorption, transmission, etc. will happen. And then the rays are reflected back to the sensor. So while talking about the sensor, we have two different types of sensor. The one is passive sensor, which uses the external source of radiation, and the active sensor provides their own source of light. So passive sensor will use the radiation from the sun in order to capture the information about various targets. But active sensors will provide their own source of illumination to capture the reflected rays. So while we are seeing about the difference between active and passive sensors, active sensors provide their own source of illumination and they work on day and night. Since they have their own source of illumination, they can work throughout the day 24/7. So some of the examples of active sensors will be the radar sat, lidar, etc. And moving on to the passive sensor, we know that it uses sun as a source of illumination. So the information can only be collected during the daytime. For example, Landsat and So next, moving on to the electromagnetic spectrum. So electromagnetic waves are arranged according to their wavelength and frequency, and this is termed as the electromagnetic spectrum. So when we are seeing the electromagnetic spectrum, we have a visible spectrum which is from 400 nanometer to 700 nanometer, where we have the colors of blue, green, and red, and the shades of blue, green, and red will be seen in the visible spectrum. Beyond the visible spectrum, beyond 400 nanometer, we have the ultraviolet, which is near to the blue spectrum. And beyond the 700 nanometer spectrum, we have the infrared, then we have the thermal infrared, then the radar, then we have short wave and medium wave and long wave, radio waves, microwaves, etc. And on to this side where we have the ultraviolet, we can see the X-rays, gamma rays, and cosmic rays. So this electromagnetic radiation, when it is interacting with the atmosphere, that is when the rays are passing through the particles which are present in the atmosphere before they are hitting the target. So there two mechanisms are happening. One is the scattering and the other one is the absorption. So particles and the gases which are present in the atmosphere can affect the incoming light and radiation from the energy source. So the first one is scattering. So the scattering occurs when the particles or the gas molecules are present in the atmosphere interacting with the energy source and causes the electromagnetic radiation to be redirected from its original. So we have three types of scattering. First one is the Rayleigh scattering. The second one is the Mie scattering, and the third one is the non-selective scattering. So Rayleigh scattering usually happens with the gas molecules which are present in the atmosphere. Mie scattering, where the diameter of the particle is larger than the gas molecules like smoke or dust. And the third type is the non-selective scattering, where the particle size will be larger. For example, water droplet. So under Rayleigh scattering occurs when the particles are very small compared to the wavelength of the radiation. So as we have seen, the small specks of dust or nitrogen and oxygen molecules will be very small compared to the wavelength of the radiation. So this is the reason that the sky is appearing blue during the day. So the sunlight will pass through the atmosphere. The shorter wavelength, that is the blue wavelength of the visible spectrum, which is the 400 nanometer range, are scattered more than the other visible wavelengths, that is green and red. So this is the reason these skies are appearing blue. The second one is the Mie scattering. So this scattering exists when the atmospheric particles diameter is essentially equal to the wavelength of the energy. So like water vapor, smoke, dust are the major causes of this type of scattering. So it occurs mostly in the lower portion of the atmosphere where the larger particles are more abundant, because gas molecules will be present in the upper portion of the atmosphere and the smoke, water vapor and dust will be present in the lower portion of the atmosphere. And longer wavelengths are visible more when compared to the Rayleigh scattering. The scattering will have a longer wavelength than the Rayleigh scattering. And the third type is the non-selective scattering, which is produced when the particles in the lower atmosphere will have a larger diameter than the radiation beam transmitted. So this is called as the non-selective scattering. That is, all the wavelength of the light are scattered, not just blue, green, or red. So the scattering will be higher. So the particles like water droplets, which makes up the cloud and fog bands, scatter all the wavelengths of visible light equally well, causing the cloud to appear white. So next, coming on to the Earth surface interaction. So once the radiated energy has been interacted with the atmospheric particles and then it has gone through the Earth surface. So the radiation is not absorbed or scattered at that stage in the atmosphere. So those types of radiation only will reach the Earth surface. So when the electromagnetic energy is incident on any of the given Earth surface feature, three energy interactions are possible. One is the absorption, second one is the transmission, and third one is the reflection. So the proportion of each will depend upon the wavelength of the energy, the angle of incidence with the surface, and the roughness of the material, and the condition of the feature. So what type of reflection will happen? So once when the interaction is happening with the earth surface. That is, when it is focusing on any one of the target. For example, if it is a road surface, uh, the surface will be smooth. So at that point, the reflection will be a specular reflection. That is, we get a mirror-like reflection where almost all the energy will be diverted from the surface in a single direction. But when the surface is having a rough texture, so we have a scattered or diffuse reflection. So the energy is reflected almost in all directions but uniformly. So this happens when the interacted surface is undergoing a reflection. So here we have a concept called spectral reflectance. So spectral reflectance is the ratio of the reflected energy to the incident energy as a function of wavelength. So various materials of the surface have different spectral characteristics. So the spectral reflectance is responsible for the color or tone in a photogrammetric image of the photographic image of the object. So tree appears green because they reflect more of the green wavelength. The values of the spectral reflectance of objects averaged over different well-defined wavelength intervals comprise the spectral signature. This reflectance is following a certain pattern for each and every distinct feature. For example, for soil, for water, and for vegetation. So it is having a peculiar reflectance pattern for each and every spectral reflectance. So that is called as a spectral signature of each and every feature. So this graph shows the spectral reflectance curve, that is the spectral signature of soil, vegetation, and water. As we could see, the dry bare soil, right from the value of 10, it is just increasing in wavelength. The reflectance percentage is getting increased till 1.8 micrometer. So after that, it is just lowering down. So soil will be reflected more because it is having a rough texture and it doesn't have any moisture present in it. Since it is a dry bare soil, the reflectance is high here. And the second one, the green one, is the vegetation. So vegetation is having more ups and downs in the reflectance compared to the wavelength of the particular visible spectrum. So the third one is the water. So water, since it is clear, it will be having very low reflectance in the visible spectrum. So this is how the different signatures for soil, vegetation, and water are identified. So for a vegetation, the spectral characteristics will vary with the wavelength. So plant pigment in leaves called chlorophyll strongly absorbs the radiation in the red region and the blue region of the electromagnetic spectrum, but reflects the green region. So the internal structure of healthy leaves acts as a diffuse reflector of near-infrared wavelength. So this is the reason the vegetations will be seen as red color in the satellite image. And the second one is the spectral signature of water. So majority of the radiation incident upon the water is not reflected, but it is either absorbed or transmitted. So longer visible wavelength and near infrared radiation is absorbed more by water than by the visible wavelength. So the water will be looking blue or blue-green due to the strong reflectances at the shorter wavelength and darker if viewed at red or near infrared. So third one is the soil. Majority of the radiation incident on the soil surface is either reflected or absorbed and a little is only transmitted. So the characteristics of soil that determine its reflectance properties are its moisture content, so the organic matter, the texture, the structure, and the iron oxide content. So the presence of moisture in the soil will decrease the reflectance. As we have seen that water will be absorbing more of the emitted energy. So the moisture which is present in the soil will decrease the reflectance characteristics. By measuring the energy that is reflected by the targets on the Earth's surface over a variety of different wavelengths, we can build up a spectral signature of the object. And by comparing the response pattern for different features, we'll be able to distinguish between them, which we may not be able to do if only we compare them at one wavelength. So for example, water and vegetation will reflect somewhat similar in the visible wavelength, but if we are seeing it in the infrared wavelength, we can identify the difference between their reflectance pattern. So this is about the spectral reflectance and the spectral characteristics. So once when the energy is reflected, it moves to the sensor. So sensors are placed in platforms in the satellite. So what is a platform? So it is a craft on which a sensing device is mounted. The vehicle carrying the remote sensing device is called as a platform. So these platforms are placed where the sensors will be present, and this will be depending upon the working environment. So platforms generally they are fixed platform or moving platform. If they are on a fixed platform, it will be in the case of a satellite. So it is cherry based or tripod based. Using a tripod, we can fix the platform. And if it is a moving platform, it may be an airborne or a spaceborne. Either the platform may be in the aircraft, or if it is a spaceborne, it will be in the satellite. So if it is an airborne platform, we can have it as a balloon based, or we can use an aircraft. And if it is a spaceborne, you can have a geostationary satellite or the sun-synchronous satellite. So considering the different remote sensing platforms, we can have three different categories. So one is the ground based, where we can have a handheld platform, but the data accuracy which is obtained from a handheld platform will be less compared to the airborne as well as spaceborne. Since it is held in hand, the accuracy will differ when it is not having a stable base. And the second ground-based platform is the raised platform, where we can have the platform on a tripod, which is having a raised platform plane. And the second one is the airborne, like aeroplane, helicopters, hot air balloon, airship, then tethered balloons, all those things. And the spaceborne will be like space shuttle or a satellite. So these are the different categories of platforms which are used in remote sensing. And this is also an example of ground-based, airborne, and spaceborne. So ground-based, we can have the platform around 150 meters, and above 150 meters, we can go for drones, aerial televisions, aerial photographies, airborne SAR, like nearly till 12 kilometers, we can use the airborne platforms. And above that, like 700 to 900 kilometers or above that, we can use a space shuttle and satellite as a platform. So once when we are knowing about the platform, next we'll be seeing about the scanners that is present inside the sensor. So the platform will be there and the sensor will be placed above the platform, and the platform it should be ensured that the platform is stable, and then the sensor should be mounted on the platform, and inside that sensor we have a scanner. So an optical scanner is an electro-optical remote sensor, a scanning device which is in most case a mechanical component. So, like simple scanners, like thermal scanners, which are operating in 7 to 14 micrometer range. So, it consists of a sensor rack, a single detector with electronics, a mirror, optics for focusing, and a storage device. So, this will be a simple scanner which is used as a ground-based or a space air-based airborne, which is used in an airborne platform. The most commonly used scanning device is a moving mirror, which can be an oscillating mirror or a rotating mirror. So alternatively, this will be used for laser scanning, that is fiber optics. The scanners are used for sensing in a broad spectral range from light to thermal infrared and beyond to microwave radiation. So while speaking about the scanner, we have two types. One is the cross-track scanner and the second one is the along-track scanner. So across-track scanner, from the image we can identify that the track is in a certain position and the scanner is moving across the track. So the scan direction is like this in a horizontal manner, and the scanner. So this is the scanner. We have a rotating mirror and a detector also, and a motor to rotate the mirror. So the field of view, the angular field of view is in this direction, and the scanner is moved across the track. So this is called as an instantaneous field of view. And the second one is along the track scanner. So the track is in this direction, and the scan is also done in the same direction as of the track. So here we have a detector array. Since it is detecting the swath, that is the direction, in the same pattern. So we have a detector array to record all these information. Using a lens and a focal plane, it will be focused. The field of view will be focused, and the scanner will be working in that. So across-track scanner refers to the process of scanning or moving in a direction perpendicular to the track of the path being followed. So the Earth is scanned in a series of lines, and these lines are perpendicular to the direction of the sensor motion, that is across the span. So these lines are scanned from one side of the scanner to the other side using a rotating mirror. So this will be functioning like how we are drawing parallel lines in the paper with a mirror. So the schematic representation of an across-track scanner is shown here. So with the help of motor, the mirror will be rotated and the angular field of view will be scanning all the information on track in a perpendicular manner. And the mechanism is like the sensor is fixed to the satellite, which is moving along the orbital trajectory and systematically gathering the data in a sequential manner. So the satellite advances incrementally after scanning each line, ultimately constructing a comprehensive image by piecing together these lines in a mosaic pattern. So once it will be mosaic, or there may be some overlap between one track and the other track. So the main application is like it is used for the Earth observation particularly and for meteorological objectives also. And the major use of this scanning is it allows for efficient and quick covering of larger regions. When you are using this scanner on a airborne platform, so it will be easier to cover larger areas in a shorter period of time. And while seeing about the drawbacks of this type of scanner is the process of acquiring data happens in separate lines, which may lead to gaps or overlaps between the neighboring lines. And the along track scanner refers to the process of scanning or imaging an area along a certain path or track. So this will be a continuous motion of painting on a canvas, like along the direction of the track. So the scanner does not have a mirror looking off at various varying angles. So instead there will be a detector array stacked side by side. So each having some time dimension on its plate surface. These may be several thousands. So we can see the schematic representation of the long track scanner having a detector array. So there will be a focal plane and the focal plane will be focused on the lens, and then the instantaneous field of view will be covering the track. So the mechanism used here is the sensor is mounted on the satellite, traverses its orbital path, conducting a continuous scan of a specific area of the Earth surface. And this technology operates in a manner to substantial mobile camera lens. So the satellite equipped with a radar imaging system often employ along track scanning in their application. And this is this produces a continuous view without any interruptions and allows a quick data collection as the satellite moves forward. Even this scanner can be used in a larger scale to collect the data as a whole. So there may not be any interruptions for quick data collection even when it is used in a satellite. And the drawback is the sensor necessitates operating at elevated velocities and maintaining exact synchronization with the satellite's movement in order to guarantee the precise data acquisition. So mainly the scanners are having various uses. So comprehending these scanning techniques is essential for effectively understanding the satellite data. So this understanding enables scientists to properly utilize the data for many purposes like weather forecasting, where the across-track scanning is used to detect the cloud formation, precipitation patterns, and other meteorological phenomena. And in environmental monitoring, both the along track and the across track scanning are employed to observe the changes in the environment, which includes deforestation, pollution, and any modifications in the vegetation. And it is also used in mapping and navigation. Like the use of these scanning technologies produce highly detailed images of the Earth surface, which are valuable for creating maps and aiding in navigation. Thank you.